Welcome, this is David Alexander, and this is an example on Chapter 6. Okay, the problem is, on a hot Chico summer day, you walk into your house, you realize that it is quite warm. The air temperature is about 35 degrees C, and you quickly turn on your air conditioning unit, and you set it to 20 degrees C, and in 30 minutes you are now cold. Okay, well, maybe not cold, but the room has decreased to 20 degrees C, and you're curious and want to figure out what is the power consumption of your AC unit. You decide to try to figure out what this unit power requirement is, and so you pull it out of the wall and you look on the back of it and you find a sticker that looks something like this. Now, this sticker has a number on it that looks something like an efficiency number, EER. That's the energy efficiency ratio. And we know this because in the book, in Chapter 6, page 286, gives us the definition for the energy efficiency ratio. And we ask ourselves, how's that going to help us? So we keep in mind that our goal is the rate of work. Okay, so we're getting smaller and smaller here. So if we want to figure out what the rate of electrical work into our refrigeration unit, we do have a relationship that relates the coefficient performance for a refrigeration unit, which is defined as the desired output over the required input. And that would be the desired output for a refrigeration unit is the cooling, and we're talking about rates, so we put a dot on the top, and the amount of work in, the rate of work in to our refrigeration unit in order to get that rate of cooling is going to be the electrical work in. So there's a relationship, and if we know COPR and we know the rate of cooling, then we can determine what our total power consumption is. And so it looks like we're going to be able to know our coefficient of performance R, and we also are looking for that, which is our goal, our power consumption. And the big question is then, what do we do with our rate of cooling? And that's going to be based on basically the change in internal energy of our room, and more specifically the change in internal energy of the air in the room, and divided by the time it takes to do that, as long as we're operating over a constant, as long as that rate of cooling is constant, which it is, then the change in internal energy divided by the change in time is going to be the rate of cooling. And we know that the internal energy is going to be the mass of the air times the specific heat of the air, and specific heat. So it seems clear that since this is just a fixed mass of air inside of a house, the house boundary isn't moving, so we'll call that C sub V because there is no boundary work associated with the input of heat and the changing internal energy of the air. We have T2 minus T1, and all of that is going to be divided by small t. Let's just take a quick look at all these terms. The mass of the air, we're going to have to figure out. C sub V is a value we can look up in the table. We probably want to look at that in terms of the average, C sub V average, and then temperature difference before and after we have, and we also have the change in time. So the mass of the air in the room is equal to the density times the volume. The volume is going to be our area times some height, and you're a college student, so let's say you live in a 10 meter by 10 meter, so 100 square meter. So the density for air is 1.2, 300 meters cubed times 1.2, and that's going to look something like 360 kilograms of air. We've got time, we've got our change in temperature, we've got C sub V, which 0.718. If I look on page 900, table A2 for air, changing from 300 Kelvin to 350 Kelvin, it changes by a fairly small amount, so we could call that, let's call our C sub V 0.72. And now we've got everything to solve the problem. And if we replace all that with our numbers, we get 0.752 kilowatt. Okay, so let's take a look at these numbers. We have 0.752 kilowatts of cooling, and we have our sticker, which looks like, if we look down at the bottom here, we're talking about a 3-month period, 8 hours a day. So 8 hours for 3 months. So what does that mean for operating, for cooling the room? If we were to maintain that 0.752 kilowatts for 8 hours, that looks like 0.752 kilowatts times 8 hours, 6.016 kilowatt hours. And let's see, if we multiply that by 12 cents, then that's times 12 cents equals 0.722 for those 8 hours. Then we're going to multiply that by 30 days and 3 months. So 90 days equals 64.97 per year, which is pretty close to the cost, the estimated cost on the energy guide. Okay, that concludes our example. Thank you.